Hello, and welcome to this video. In this video, we're going to do an introduction to this idea of forces, and we're going to see how do forces behave and why do they cause things to move. And that is all based on Newton's laws. So Newton was the person who came up with all of this idea of gravity and all of these forces that are acting. And so we're going to use Newton's laws for the majority of this section of the course, just to be able to describe how things begin moving or how they stop moving or how they change motion. But before we get into stating what Newton's laws are, we have to first define a few things. So the first thing to do is we're starting this topic of forces. Are they scalars or vectors? And we should know that all forces are vectors, okay? Because I don't say that there's a force of 10 newtons. I would say that this is being pushed 10 newtons in this direction. So if I had an object here, it would be pushed in that direction. Therefore, it has to be a vector. Okay. The second thing we have to look at is what do we mean by resultant forces? How would we calculate a resultant force? So a resultant force is just the overall effect of all of the forces combined. So it's the overall force acting on an object. So we take into account all of the possible forces that are acting on this object, and we narrow it down to, if we were to cancel out some of these things, what would the actual effect be? So for example, let's take this object again. Let's say something is pushing it in this direction with a force of 10 newtons, and something is pulling it back, maybe friction, pulling it back in this direction with 7 newtons. And we would say the overall force, hence the resultant force acting on this, is just going to be 3 newtons acting in this direction. Okay, it's simply you just take the smallest one, they take the biggest one minus the smallest one, because we know this is going to overpower this force, and so the overall motion of this is going to travel in this direction. And this is the base of everything we're going to do from here on out. Okay, so now let's look at what are Newton's laws. So we should know that there are 3 laws. So the first law is saying that if there is no resultant force present, so if there is no resultant force, this means that the object must be either stationary or traveling at a constant velocity. Okay, so this is Newton's first law. Okay, a lot of you will have already seen this already. But what this means, if there's no resultant force, that doesn't mean that there is no force, no forces acting on this object. It could still have forces acting on it. So for example, if we had that box example back, and this is then being pulled with 10 newtons in this direction, if the friction coming back is also 10 newtons, then they completely cancel each other out. And that means that there's no overall force, so that the resultant force here is 0 newtons. So we have no resultant force. So this object is either stationary or it's traveling at a constant velocity. Now, how do we know whether it's going to be stationary or traveling at a constant velocity? Well, it all depends on what is it initially doing when these forces become balanced. Okay, and this is the idea of inertia. Okay, so inertia is usually described as just the tendency of an object to remain stationary. So if it was already stationary and then we applied equal forces, it will remain stationary, or to keep traveling at or just to keep moving, I guess. So inertia is basically the tendency of an object to just keep doing what it's doing. So if it's already stationary and then we apply equal forces, we're not really changing anything because we're applying 0 overall force, so it's not going to change anything. So if it's already stationary, then it's going to remain stationary. If it was already moving, doesn't have to be moving at constant velocity. If it was already moving and then we introduce these balanced forces, it will continue to move, but it will not accelerate anymore. It will have to travel with a constant velocity. Okay, and this is the first law. So this is this kind of useful law for when we're going to look at how do we identify when something is in equilibrium. Okay, so when it's in equilibrium, it basically means we have no overall forces, and so we're going to use this first law in those cases to try and figure out what certain forces have to be in order to make something in equilibrium. Okay, so this is the first law, and that takes us on to the second law. What happens if there is a resultant force? So the second law is that, well, let's just go with second. If a resultant force is acting on an object, the object will accelerate. Okay, now this would have mostly seen in the form of an equation rather than words, and we can say that this basically means that the force here has to be proportional to the acceleration. So if we're applying a force to it and it's causing it to accelerate, then surely if we put a higher force in, we're going to get more acceleration, and if we put in a lower force, we're going to get less acceleration. So we know force and acceleration are related, and so the relation that we should already be familiar with is this idea that F is equal to the mass times the acceleration. Okay, so this should already be a very familiar formula for you, and this is going to help us a lot with this. This is kind of a fundamental thing that always works, and so it will help us more when we're going to use this idea of forces and start to transition into looking at the motion variables. So we said the motion variables were the displacement, acceleration, velocity, time. That's going to help us in that case. Okay, but this means that if I have what I started with, and let's say, for example, this is 10 newtons. Let's say this block had a mass of 2 kilograms, and there were 7 newtons acting backwards. I know my resultant force, which is what this F means, is 3 newtons, and that 3 is equal to 2 times A, so that means my acceleration of this block as it moves is just 3/2, or 1.5 meters per second squared. Now I want to say something here. We'll repeat this in the motion videos, but if this force is a vector, which we know it is, and mass we should know is a scalar, then in order for this to be a vector, this acceleration also has to be a vector. Okay, so we accelerate in that direction. Okay, which means if we have a negative force, i.e. the force is traveling in the opposite direction, that means we'll have a negative acceleration. Now all negative acceleration means is deceleration. Instead of its velocity increasing, its velocity is going to decrease, so it just slows down. Okay, so you can get positive and negative forces, and you can get positive and negative accelerations, and the positive and negative forces and accelerations, because they're vectors, just describes which direction they're moving in. Okay, that means that for all of these problems, we have to start by setting up some sort of base coordinate system. Okay, for this case, it's kind of obvious what we've done. Because we've said that this is going to be positive 3 newtons, we've defined this direction to be the positive, okay, which means this 7 is a negative. Okay, so we've basically said that this is minus 7 newtons, and to get the total force here, we've just added them up. So we've just said 10 plus minus 7 is equal to 3, and so we know the resultant force is actually traveling in the positive direction, and that means that we can get our acceleration is in the positive direction as well. Okay, so this idea here of setting up an axis to define it to be the positive is going to come in very, very handy for most of these things, especially since we're always working with vectors. It's really easy to get things wrong just by missing a minus sign somewhere, or just having the wrong variable in the wrong direction. And so if we just start the question by setting up our axis, defining one direction to be positive, it will make sure we get everything else nice and easily. And then the final of Newton's laws, the third law, is possibly the most famous of the laws. It is that every action has an equal and opposite reaction. Now, so it has an equal and opposite. Most people will have taken this to be almost philosophical, I guess, because some people will say that this applies to everyday life. If you do something, something's going to come back to you. But this isn't philosophy. We're only interested in the physics. Okay, so we just know what we mean by actions in this case is an action is a force. So if I push something, that is an action that I've done to that object. And this means that if I push this object, so let's say this is a wall. Actually, let's make this just a wall, and this is my hand. I'm not very good at drawing hands, so I'm just going to put it as a box. Let's assume this is my hand on my arm or a foot, whatever it is. If I push on this wall with some force, the wall doesn't move. Okay, and we would say, well, why doesn't the wall move? Surely if I'm pushing on it, there's a resultant force that acting on that wall, and so it should move. Why doesn't everything move when we instantly push it? And that's because of this reaction force. If I push on the wall with some force F, the wall is going to push back on me. That's why we don't go through the wall, because the wall actually exerts a force back on us. So if you push the wall with enough force, you'll actually move backwards because the wall is pushing a force back on you. And this is the reaction force. Okay, it will be the same for things like, let's say this is a table, for example, and then we put some big mass on the table. This mass has some weight acting down, but the reason it doesn't just fall straight through the table is because the table is also pushing back up onto this mass with the reaction force. And the fact that they're equal and opposite means that this reaction force is actually equal to the weight in this case. Okay, and this is also a very helpful thing, because it helps us to understand why certain things don't move if we push them. So like the wall example, or why is it if I push off a desk, if you put your hand on the edge of a desk and then you extend your arm, why do you move backwards? Why doesn't the desk move backwards? Okay, you're applying the same force, but your masses are different. So this can actually relate back to the second law, and say if I'm applying a force to this desk or this wall, I'm trying to accelerate that, but since the wall has a much higher mass, the acceleration is almost zero. When the wall applies the same force back on you, your mass is a lot smaller than the mass of the wall, so your acceleration will be a lot higher in order to make the force the same. So that's why things move, okay? Or some things don't move, I guess. And these are Newton's laws, okay? So our first law is that if we have balanced forces, we have no overall resultant force, then that object will either remain stationary or it will continue to move with a constant velocity. Our second law is if there is a resultant force acting on an object, that object will accelerate, and we simplified that whole law down to F equals ma. And then our third law is that if we apply an action to something, that something will apply an equal reaction back to us, just in the opposite direction, but equal magnitude. And this is going to help us when we look at this whole topic of forces. Thank you for watching.